Well, hey everybody. This is a problem that was requested to get worked out. You see this problem in lecture 6C right towards the end. And the question says, if we were to make a standard battery out of aluminum and nickel, we should be able to find the cathode, the anode, the oxidizing agent, the reducing agent, the overall reaction, the direction of electron flow, the number of electrons transferred, and the cell voltage. So it sounds like an awful lot of things to try to find just from knowing all we have is aluminum and nickel, but we can do it. And so let's go ahead and get started. First thing we want to do is let's just go ahead and look up our elements. And I've already gone ahead and written them here. So we've got nickel and aluminum. Now, we weren't told the charges, but luckily these two elements pretty much only form these two charges. It is possible to have nickel in a +1 state, but it's pretty rare. So we just go ahead and default to the most common here, which is nickel 2+. And when you look up the reduction potentials for nickel and aluminum, we see that we have nickel 2+ 2 electrons going to nickel metal, and that has an E0 of minus 0.25 volts. And for aluminum, we have aluminum 3+ 3 electrons going to aluminum metal, and that has an E0 of minus 1.66 volts. So we're going to use that information a little bit later. First thing we want to do, however, is let's go ahead and draw out our battery. And so as usual, we're going to have our two beakers here. So there's one, there's two. I'm going to put a solution into one of them. And so my nickel solutions tend to be kind of greenish blue. So I'm going to put the green over there. Aluminums don't really have any color at all. So I'm just going to put a little gray solution there for the water. So for our nickel, I'll put a blue electrode coming out here. And so that is my nickel electrode. And I'll have my aluminum electrode here. So this is my aluminum. This is my aluminum 3+ solution and my nickel 2+ solution there. We need to connect the wires with, or the two electrodes with a wire. So here's my wire here. I'm just going to put a little voltmeter there in the middle, just because I like to do that. We want to add a salt bridge. I'm just going to add a salt bridge just kind of like this in between there. And we always have these little, what are called fritted glass plugs in here, so it's porous glass. So it keeps the solutions from just pouring into one another, but it does allow ions to pass through there. So that would actually connect the two beakers together. Okay, and there we have our cell. Now, by looking at some of the information that we have from the two half reactions, we can figure out which way the voltage is going to go. We can figure out what's going to be oxidized and what's going to be reduced. Now, since the nickel has the higher of the two, or the more positive or the less negative half cell potentials, that means that nickel is more likely to be reduced. So that is what will be reduced. So the nickel will be reduced and the aluminum will be oxidized. Okay, so we know that the nickel will be the site of reduction. The aluminum will be the site of oxidation. The site of oxidation is always the anode, which means that the site of reduction is always the cathode. And an anode, just like an anion, is always negative. So we've got the signs here, and our cathode here will be plus. Okay, so let's see what we've taken care of so far. We've taken care of our cathode. We've taken care of our anode. We don't have much of anything else. We can do the direction of electron flow. Electrons always flow from the anode to the cathode, or as I like to say, they go from A to C, because your anode is a site of oxidation, so that's where electrons are being lost. So electrons are going to be coming up from the aluminum there, crossing through the wire, going through the voltmeter and coming down and depositing a nickel ion onto the nickel electrode. And so we now have our direction of electron flow. So we've got that one now too. Okay, we can do a couple of other things. I may need to go to the next page, but I'll see what I can squeeze onto this page first. We can look at our oxidizing agent and our reducing agents. And so we know that the nickel is being reduced. We know that the aluminum is being oxidized. So the thing that is being reduced means that it is the oxidizing agent. Now, when we say something is an agent, we're really looking at what is it doing to something else. So when we say something is oxidized, that's what happens to it. When we say it's an oxidizing agent, that's what it's doing to something else. And so since nickel is being reduced, that means it's gaining electrons, but it also means it's making something else get oxidized. It's taking electrons away from something, so it's making something else get oxidized, which means it is the oxidizing agent. So our half cell over here is the oxidizing agent. Actually, it would be the nickel 2 plus that's the oxidizing agent. Because it's what's gaining the 2 electrons. And my reducing agent then would be the aluminum metal, because it is causing something else to be reduced. It's causing something else to take its electrons and gain them. So your aluminum here is the reducing agent. Okay, so we've got the oxidizing agent and the reducing agent taken care of. All right, and so next couple of things that we need to do, the overall reaction, the number of electrons transferred, and the cell voltage we still need to do. Now, in order to get the overall reaction, we need to write the reactions as what's happening to them. So we're going to write the nickel reaction as a reduction reaction, half reaction, because that's what's happening with it. So let's go ahead and do that. Let me try to pick a different color here. I guess I'll do the red here. So we've got nickel 2 plus 2 electrons going to nickel metal. And we want to write the aluminum as an oxidizing reaction because the aluminum is being oxidized. So we're going to say aluminum is going to aluminum 3 plus 3 electrons. Now, in order to get a proper reaction, I have to make sure that when I add these two half reactions up, I don't have any extra electrons left over. So that means I have to make sure that I multiply both of the two half reactions by some factor so that when I add the two half reactions together, we will get no electrons left over. And so I use the lowest common multiple method here. I have 2 electrons in my top reaction, 3 electrons in my bottom reaction. So the lowest common multiple between 2 and 3 is 6. So I need to multiply my nickel reaction by 3, and I need to multiply my aluminum reaction by 2. And that will give me 6 electrons here, 3 nickel 2 pluses and 3 nickels. And that will give me 2 aluminums, 2 aluminum 3 pluses, and 6 electrons. And now when I add these two reactions together, what I'm going to get is 3 nickel 2 plus 2 Al goes to 2 Al 3 plus 3 nickel. Okay, so there's our balanced reaction. As far as the number of electrons transferred, the number of electrons transferred is that lowest common multiple that you needed. So here we had to have 6 electrons in order to cancel out, to add two half reactions together. So that means that my N value, number of electrons transferred, would be 6. I had 3 nickels losing 2 each, so or gaining 2 each, so they gained a total of 6 electrons. I had 2 aluminum atoms losing 3 electrons each, and so they lost a total of 6 electrons. So a total of 6 electrons were transferred. So we've got our number of electrons transferred, and we've got our overall reaction. Now for the cell voltage, what we need to do, and I'm going to go to the next page here, For overall cell voltage, we want to use the equation E0 cell is equal to E0 cathode minus E0 anode. Now, when we use this equation, we only use reduction potentials. That's very important. Okay, even though the aluminum is the anode and it's undergoing oxidation, we've taken care of that with the minus. So we're still going to use the reduction potentials. So for our equation here for E0 cell, we say that E0 for the cathode is minus 0.25 volts minus, and now we need to use the E0 for the anode, so it's a minus a negative 1.66 volts. And when we do that, we get a positive 1.41 volts. And so this is my cell potential for this cell. Now notice something I did here or didn't do is I did not change the values of my E0 cathode or E0 anode. Even though the cells themselves had to be multiplied by 3 and by 2, your cell voltages are intrinsic properties and they don't change with the amount of material that gets used. And so we never multiply those half cell voltages by whichever value we needed to balance out the reaction. So make sure that you leave those alone. You use them exactly as they're in the table using this method. You use only reduction potentials and you don't have to manipulate them at all. So if we go back here, we found the cell voltage, oxidizing agent, reducing agent. We found everything in here. Okay, well, hopefully that helps you with the nickel aluminum problem. As always, if you have questions, please make sure that you contact me.